Right, so or not yesterday, but the day before yesterday, we ended off with this question. We kind of were going through it really quickly because we were running out of time. So I'm just going to set it up again. Okay. So in this question here, we have a bullet accelerating through the length of the barrel of a gun, which is 0.750 meters long. Okay. So it's a rifle, obviously, not a pistol. Okay. The acceleration is massive. Okay, it's 5.35 times 10 to the 5 meters per second squared. Right? That would liquefy you. Okay, if you were undergoing that kind of acceleration, you would be a puddle of poo. Okay, it's a massive acceleration. But you have to consider that when a gun is fired, the bullet accelerates from rest to well over 3 times, or close to 3 times the speed of sound, over 75 centimeters. Okay, that's a massive acceleration. It has to be. Okay, it also leads to kind of a scary thought. I think we talked about this the other day, in that a bullet travels faster than the sound of its firing, which means you never hear the bullet. Actually, you might hear the bullet hissing, but you probably won't. Okay, you won't hear the bullet because the sound of the shot is not going nearly as fast as the bullet is. Okay. In fact, the world record for longest kill shot by a sniper is held by a Canadian. Okay, yeah, a Canadian sniper, okay, using American ammunition. But a Canadian sniper, okay, shot and killed a Taliban fighter in Afghanistan at a distance of nearly 4 kilometers. Okay. 4 kilometers, guys. I want to give you some idea. Like, if you look out the window, okay, that's way past Northridge Drive. That's through Darcy Ranch, past the golf course from here. That's scary, okay? That somebody can see you and shoot at you and, scarily enough, hit you from that distance. Okay? Now, the weird thing is that if you've ever seen sometimes they have like gun camera footage and things like that. When they're shooting at people from great distances and they miss, the people's reactions are, it's very clear they did not hear the shot. Okay? Because instead of going like this to look for where the sound of the shot is, they look at where the bullet hits the ground. Because that's what they hear. So they're looking at the ground, then they hear crack, and then they do this, okay? And they look in the direction of the shot. If it's fired from an unsuppressed weapon, okay? Most of the time, snipers would be using a suppressed weapon if they were trying to stay concealed, okay? So you would really never hear the sound, because there's really not one to hear.
Can we change this class to like military history?
No, we can't. But it's still like scary in a physics perspective. Well, we're going to do projectile motion next. That's the next thing we do when we talk about projectile motion next. Possibly. Now, a sniper's calculations are different. They've got windage, they've got drop, they've got all kinds of things. Right? And over 4 kilometers, if you're shooting across like a valley, you could have winds going in different directions on either side of the valley. You've got every second the bullet is in the air, it drops 4.5 meters, okay, or more, okay, so there's all of that to factor in. And if it's in the air that long, even the earth will rotate underneath it as it travels. Yeah, so when someone can make that shot, they are very scared. You don't want that person to not be on your side, right? Yeah. That's not the person you want shooting at you. All right, so we have this bullet, and it's going through the barrel of a gun, and obviously bullets are not moving when they are fired. Okay, we kind of take that for granted. Okay, 0 meters per second. Okay, we know that the acceleration is that massive number, 5.35 times 10 to the 5 meters per second squared. Okay, and the distance it travels is 0.750 meters. So we're looking for the final speed, in this case, because it actually says speed, we're not given any vectors here, of the bullet. Right? So that means we're using the formula that we used just a minute ago, okay? And that's VF squared equals VI squared plus 2AD. Okay? And we're looking for VF. So the only manipulation we have to do is to solve for VF, not VF squared. So that'll be VF equals the square root of VI squared plus 2AD. A very common mistake I see people make here is that when they put the square root here, they take this square off. Should you? No, it's like this is in brackets. You're square rooting the entire thing, okay? Not square rooting everything, because otherwise it would be VI plus the square root of 2 plus the square root of A plus this, or yeah, it's a mess. We don't do it that way. Okay? All right, so now we just plug in our numbers here. So VF will be the square root of 0 squared, because it was starting from rest, okay, plus 2 times that massive number, 5.35 times 10 to the 5, times the distance over which the acceleration occurs. And remember, the bullet is actually only accelerating, like speeding up, as long as it's in the barrel. Once it leaves the barrel, it's actually slowing down. Yeah, okay, because in the barrel, there's a force, the force of the expanding gases pushing on the bullet. Okay, but once the bullet exits the barrel, all it has is the force of resistance of air, slowing it down after that. Right, so when we're looking at this, okay, we will have the square root of 2 times, and then our big number here, 5.35 times 10 to the 5, and times 0.75. Okay, so that bullet leaves the barrel at 896 meters per second. Okay, that is very nearly 3 times faster than sound. Okay, like some of the fastest aircraft that we have built can go that fast. Okay, that's nearly Mach 3. So very, very fast. All right. Questions on how that one works? Okay, I want you guys to try these two here. They involve using that formula. Right, so give those ones a try, and then we'll go through them together here in a minute. Okay, let's have a look at question number 1 here first. So we have a jetliner that lands on a runway at 70 meters per second. So that will be our initial velocity, or initial speed, I guess, because it doesn't give us direction on that. Okay, it reverses its engines to provide braking and comes to a halt. Okay, that's one of those things you got to be watching for. Okay, when they give you a number but don't give you a number. Okay, in that case, and it does that in 29 seconds. Okay, so we want to find out what's the jet's acceleration. Well, that involves actually using last year's formula. Okay, that's how I would find acceleration with those 3 things. Okay, Vf minus Vi over T. So that would be 0 minus 70 divided by 29. Right, and that should give me negative 2.4 meters per second squared. And I do have to leave that as negative. They didn't give me east or west or north or south or anything like that. So all I have is negative there. Right? So that would be that one. For B, what length of runway did the jet require to safely come to a complete stop? All right. There's a couple of ways for me to do this question, for me to do part B. Because I now have VI, VF, T, and I have acceleration, I can use any of the acceleration formulas I want. Okay? As long as they have D in them, that's what I'm solving for, I can use them. Right? What I try to do, if I can, is I try not to use numbers that I calculated, just in case I screwed up. Okay? So the formula I would use for this one would be this. D equals VF plus VI over 2 times T. Okay? That doesn't involve me using acceleration. Now, I know I calculated acceleration right. I could use any of the other formulas, but this one will get me D without having to use the acceleration I calculated. Okay, so that would be 70 plus 0, 0 plus 70, doesn't matter, okay, over 2 and times 29 seconds, right, and that should give me 1 kilometer, okay, or 1.0 times 10 to the 3 meters when I do that. All right, questions on number 1? How many people have done number 2?
I don't know.
Okay, we'll get going on number 2 then. So on number 2, the first thing I need to do is I need to convert the 2 kilometers per hour values into meters per second. All right, so it's going to increase from 50 to 100. So VI is the 50. Okay, so if I go 50 divided by 3.6, All right, I'm going to get my meters per second, so 13.88.
That's by 1,000.
I times it by 3.6. That's by 1,000 and divided by 3,600.
Okay, so then VF will be twice that number. So 20,
Where did you get 3.6?
27.7. Where I get it from is from where I told you to get it from the other day when I went through explaining how to convert one to the other. Okay, this is what I did, just as a quick review. If I have 50 kilometers in 1 hour, I have to convert first the kilometers by multiplying by 1,000. That'll convert kilometers to meters. Then I need to multiply by a conversion factor that will convert hours into seconds. I divide the number of hours by 3,600, okay? Or sorry, multiply the number of hours by 3,600 and I get seconds. So if I take the number I have, multiply by 1,000, then divide by 3,600, I'll have my value in meters per second. But I can shortcut that by saying it's the same as multiplying by 1 over 3.6, which is the same as going 50 over 3.6. Agreed? So if I divide by 3.6, I get meters per second. I multiply, I go the other way. Okay. So now that I've got those two, okay, this is meters per second now, this is meters per second now. Okay, we know the acceleration is 3.8 meters per second squared. And that's got to be positive because it's increasing in speed. Then I can figure out the minimum length of the on-ramp. And this is very similar to the calculation that any like city planner, road designer would use in order to determine the proper length for an on-ramp. Okay, in Calgary, they don't always do this. Okay, in case you've seen some of the overpasses on Deerfoot Trail, okay, you know that it's cheaper to build terrible overpasses that have stoplights at the top, okay, and back traffic up onto a 100-kilometer-an-hour road. Or they, try and sell a triumph of parent planning genius that took one set of stoplights and replaced it with 4. Okay, yeah, that's the one at 162nd. Okay, right that way. That first one when you come in. Okay, yeah, that's the dumbest thing ever. 1 set of lights, now 4 sets of lights. Oh, and traffic circles work great. The problem is North Americans don't know how to use them.
The lamp, the light.
Oh yeah, that thing too. Yeah, that's done. Okay, so if we're looking for D, okay, then we're going to use this formula here. VF squared equals VI squared plus 2AD. So if I want to get D by itself, the first thing I do is subtract VI. So I'll have VF squared minus VI squared. And then I'll divide both sides by 2A to leave D by itself. Okay, when I plug in my numbers, that's going to be 27.7 repeating squared minus 13.8 repeating squared divided by 2 times 3.8. Okay, when I do that, I should end up with 76 meters, okay, as the minimum length of the on-ramp. Yes, if you forget to square them, you will not get the right answer. All right, questions on how that one works? Okay. Try this one. It seems like it doesn't give you very much information, but you have to use the context of the question to get some of the numbers. So lots of times, in an acceleration problem, we have to look at the context of the question to get the information we need. It says a bolt falls off of a roof. Okay, if something just falls, it's not thrown, how fast was it going initially? 0. Okay, so we know its initial velocity is 0 meters per second. They don't outright say that, but the context of the question allows us to conclude that. Okay. Also, since it's falling, its rate of acceleration is gravity, right? So 9.81 meters per second squared in a downward direction. Okay, and it says the roof is 6 meters above the ground, which means this thing falls 6 meters down. right? Same direction as the acceleration, because we got to put vectors in here, right? So t equals 6.0 meters down. We're looking for how long it falls. Looking for time. Okay?
Don't we have velocity final too?
Nope.
But it'll be zero.
No, that's after it hits the ground. This is the instant it hits the ground. How fast is it going the instant it hits the ground? Okay? Because there's a whole other acceleration that happens after it hits the ground. Okay? All right, so we have, okay, VI, A, D, and we're looking for T. So in my mind, that says, here's the formula I need to use. Except, I told you you'd never have to use that formula to solve for T, unless VI is 0. Okay, VI is 0, so that means this part of the formula isn't there, and now there's only one T in this formula. So I can solve for it by simply dividing both sides by half of A, and then square rooting. So I'll have the square root of 6 divided by 1/2 times 9.81, and that'll give me how long it falls for in seconds. So square root of 6 divided by 4.905, that's half of 9.81. Okay. All right, it's going to fall for 1.1 seconds. Okay, that's 6 meters in a second. That would hurt. Okay, you wouldn't want to fall that far. But that's how far you would also fall in 1.1 seconds. Because all things, right, fall at the same rate. Now, that's obviously kind of in the perfect physical world. There's more air resistance for certain objects than others. But for all intents and purposes, it's true. Okay? Unless you're comparing like a feather and a bowling ball. Okay? Then obviously a feather is designed to catch as much air as possible to allow a bird to fly. So you drop a feather, it does this, right? Okay? But you drop a bowling ball, it falls straight down. On Monday, remind me, and I'll show you a video of a feather and a bowling ball falling at exactly 9.81 meters per second squared in a vacuum chamber. It's weird to watch a feather do this, as opposed to what we know a feather should do. Okay. All right, so we got 1.1 seconds as our answer there. Okay, making sense?
Yes.
This is exactly the kind of thing you would get on a quiz or a unit exam. I give you just an acceleration problem. You got to figure out what formula to use, manipulate, plug in the numbers, and solve. Okay? Now, acceleration problems are not just going to be in here on their own. They're also going to be part of projectile motion. Right? And that's the last thing that we go over in this unit, and we'll be starting it next week sometime. All right, try this one.